All right, so just a little reminder about average rates of change. All right, so I'm going to talk about it in general, then I'm going to talk about specifically with regard to velocity. So the average rate of change of any function on some interval is f of b minus f of a over b minus a, which looks a lot like slope, right? And that, at this point in your mathematical careers, that should make absolute perfect sense. If someone says a rate of change, you should be thinking, oh, you're really saying slope about some graph. Is that all right? Okay. We're going to have another name for the rate of change, and we're going to talk about the rate of change at a point, and we're going to call that the derivative. And the derivative is just yet another name for slope. We're not going to call it the derivative yet, but in time we will. So, do I have physics friends in the classroom? Only 1, 2, 3. All right. One of the famous rates of change. We actually talk about 2 really famous rates of change in physics, and you're probably talking about it now: velocity, right, and acceleration. We're going to talk about velocity right now. So we would say that the average velocity on some interval, let's see, is going to be, I'm not writing this very well. What's the function s represent in this case? There's a wrong answer and there's a right answer, so can we first do the wrong answer? What's the wrong answer for what s represents? It definitely does not represent speed. That's the wrong answer. There's another one that I was thinking that people might say that it's close to speed, but it doesn't start with s at all. No. I was hoping, velocity. So I was thinking someone would think, oh yeah, speed or velocity. The average velocity is the change in velocity over the change in time. That's totally wrong. The average velocity is actually, give me a unit for velocity or speed. Miles per second, meters per second, miles per hour, kilometers per hour. If you think about that as a rate of change, it's the rate of change of what over what? Distance with respect to or over time. So, Betsy, calling someone to tell us what is the s of x function.
Distance.
Just clarifying, okay? So that's like the distance or the position function. So the average velocity is the change in position over change in time.
That little triangle.
Yeah, you've seen that. Have you seen that?
Yeah.
And maybe we even would write like change in position over change in time if we weren't being so mathematical. A common misconception is that some students actually do think that the average velocity is the change in velocity over the change in time. Actually, the change in velocity over change in time has another special name, acceleration. Okay, so that's not the case. All right, is that okay? So we're actually going to look at average rates of change, and we actually did this last year. One of the things that we're going to be looking at, though, is what happens to that average rate of change when A and B get closer and closer and closer. And we'll take a look at an example. So let's look at this skiing table, and it's the distance traveled by a downhill skier for first 10 seconds. Calculate the average velocity for the first 10 seconds. Can someone do that without their calculator, just looking at the table in their head? Asa, what'd you get?
33.27.
Yeah, how'd you get that?
Because you're just doing, you're doing 332.7. You're doing that minus 0.
Okay.
You're doing the first 10 seconds. And then you're doing that over 10 minus 0. So essentially you're just getting 33.27 over 10.
Great.
Which then you divide by 10 and just move the decimal over.
All right. So what are units on this?
That'll be feet per second.
Feet per second. And that's a unit of velocity. Yeah. That works out well. So you can see that the average rate of change of position is a velocity. All right. So let's see. Can Can I have like? It's going to be a little unfair. What can we do? 1, 2, 3, 4, 5. We can do boys against girls. Good. All right. So can girls do the first 5 seconds interval B? Question B. And boys, can you do the interval from 5 to 10? I wrote that in the wrong place. Who has the easier job?
Girls.
They do. Why? I agree. No. You're just doing C. 1, 2, 3, 4, 5. Now it's really unfair because there are more girls. Betsy? 20.8? Do I have a second from girls on that? No, girls. 16.7?
I just did 15. Oh, I did 4. Sorry.
Oh, you did the first 4 seconds. All right, so we have, 16.7 you said? Feet per second?
16.64.
Okay. Hold on. Without even doing it, I know the boys did it, so don't look at the boys' answer. Girls, would you expect part C to be greater than, equal to, or less than 16.64? Why? You're right.
Because of their numbers.
Wrong reason.
Yeah, they're
Tom. Yeah, you're right, but say it another way. Don't say it so fancy using physics terms. What's it doing? Yeah, I know, but don't use a physics word. What's happening to the speed? Speeding up, right? Wouldn't you think that would happen if you're going downhill? You'd speed up. So we're speeding up. We would think the boys would get a bigger answer. Boys, what'd you get?
49.9.
What do we have?
49.1.
Do we 49.8, 49.9? Is that an agreement or not really? Zach? All right, 49.9 feet per second. So that makes sense. It's speeding up. So did we just answer part D? The skier's getting faster, and that intuitively makes sense as well. Does it make sense that the average velocity for the first full 10 seconds is somewhere in between the girl's answer and the boy's answer?
Yeah.
I think so. Right? All right, let's do boys and girls again. Actually, you know what? Here's what I'll do. I'll do E, and then boys do F and girls do G because girls starts with G.
I know this makes sense, but if you add the two together,
Oosh. Yeah, okay, fine. Betsy has an interesting observation to make. I gave you guys the easy job. Mine's hard. Why did I take the hard one?
I'll do yours anymore.
Why is yours easy? What are you dividing by?
1.
Yeah, you are. That's not fair. I'm always making it too easy for you. All right. I got 19.95. All right, so that's what I got for the average. What do you think the boys are going to get? An answer that's greater than, less than, or equal to for 2 to 3 seconds. Yeah, why less? You're absolutely right. Gabby, talk to us.
speed is increasing, like as you get bigger, and so like the difference between like the speed from 2 to 3 should be a lot less.
Yeah, if 2 to 4 is the whole thing, and we know we're getting faster, we would think then that 2 to 3 would be less, 3 to 4 would be more, and the whole thing would be like, as Betsy would say, what mathematical word could you say? 2 to 4 might be the average. I like that. Okay. All right, boys, what'd you got?
16.66.
Girls, what'd you get? And Betsy would actually say, if you took the boys' answer, the girls' answer, added them up, divided by 2, you'd get the average, 19.9. You have to 9.5. You have to divide by 2. Okay. So I have a question for you then. If someone asked you, based on what we just found, in E, F, and G, if someone asked you, how fast is a skier going at 3 seconds? Not at an interval, but actually at a specific time. I'll tell you one thing. What's the problem? What's the change in time at an instant? There's no change in time. Right? So we're saying, oh yeah, you're supposed to do change in position. Whoops. Now it's not erasing. You're supposed to do change in position. Now it's not writing. Over change in time. But at an instant, like think about it. Here I am. I'm just like frozen at that instant, right? Like a photo finish at the end of the race. Those people are moving, right? But it's an instant of time where time's not moving and it doesn't look like their position's moving. But we know they are moving. How weird is that? Like, isn't that bizarre? So what might you say? Like, what would your guess be based on? You think it's 0? Is the skier really going 0 meters per second? What? You can't do that.
Can't you say that he's at his highest velocity when...
Can I rephrase the question? Judging on the information from E, F, and G, what would you say?
19.95.
Somewhere in the middle? Like if the boy said for the from 2 to 3 seconds, the skier was going 16.6,
Yeah, so
and then the girl said from 3 to 4, the skier was going 23.3 feet per second?
So then you...
Probably somewhere in the middle. Do you want to ask a question about that? People don't seem okay with it.
What makes...
You would think 19.95 for that?
Yeah.
That's what I would say.
Exactly. That's
Because
like
also-
between 2 and 4.
Between 2 and 4 is 3.
Okay.
Uh,
Go ahead.
You could also solve it out as 23.3 minus 16.6. Like, you could take the time in between that and divide it by 2 and add that on to 16.6.
Yeah, it's the same thing as Betsy's average,
Yeah.
really. Can you see that maybe what I would ask you to do would be, why don't you look, if the table is better, why don't you take the average velocity between 2.9 and 3.1? Right? Or what about the average velocity from 2.99 to 3.01? Do you see how that's a little like the limit problems that we were doing? Like, let's take a smaller and smaller and smaller interval. And actually, Newton came up with a method of taking smaller and smaller intervals, and he came up with actually an algebraic method to make that all work. So even though you think you're dividing by 0, you're actually not. And I don't know if you remember, but do you remember like a day or two ago when we had like h in the bottom, and we had the limit as h was going to 0, and we couldn't just plug in, but we did a little bit of mathemagic, and then we could plug in? Does this sound familiar or no, not at all? Okay, fine. Yeah, so we're going to do some mathemagic later on. Not ready yet. All right. So we are going to talk a little bit about this idea.
Exponential, was that an exponential? Or like, it just like, it just
Oh, actually,
random numbers. 'Cause, like, what if you
Yeah.
made it into an exponential problem, then couldn't you figure out what 2.99 is?
Yeah, you could. You could model this. You could do like an exponential regression fit or something. And this I think this is not exponential but quadratic. So I think it's like something x squared would be my guess. So we're actually going to talk about what it means to have a slope at a point. And even though we're dealing with functions that might not be linear, we can still talk about whether the slope at a point is positive or negative, whether it's really steep or not so steep. So let's take a look at 2 and talk about slopes at points. And do you agree that's a new concept? Oh, I don't know what that is. Like, we've never really talked about the slope at a point. We've talked about the slope between 2 points or the slope of a line, but never really the slope at a point. Let's see. Tali, read for us. All right. What integer value of x does the graph have each of the following slopes? So the first thing I'm going to do is look at the integer values. So that's like 0, 1, 2, 3, 4. Do you agree that those blue points represent the integer values of x on the function? Is that okay? All right, so now I need to figure out at which points is the slope -2, -1, 1, 2, and 7. Do you agree that this curve, this function, actually the slope always seems to be changing? Yeah, I think so. But we can still talk about when the slope's positive, when it's negative, and the relative magnitude. Just as a tip, right? Positive slope means the function is increasing. Negative slope means it's decreasing. All right? So let's see what we can do. What do you want to pick? You can either pick a letter or you can pick an integer value of x. Kaylee, we want to start us off?
Okay, I'll start with A.
Okay, so we need a slope of -2. Before you do it, tell me the two places where it looks like the slope is negative on this graph.
At 0.
At 0? Are you sure? What does negative slope mean? We just said it. Decreasing. So give me the two x values, integer x values, where the function is decreasing. I would say x equal... Alright, go ahead.
1.
At 1 and at 3. And I exaggerated a little bit there, but can you imagine if we zoomed in at 1, but that actually doesn't look like a curve so much anymore, but it looks a lot like a line. And if I zoomed in on 3, it doesn't look like a curve so much, because it looks like a line. Is that alright? That's actually a property of well-behaved functions, and we'll talk about what well-behaved means later. But they have something called local linearity, which means that even though they curve, if you zoom in a bunch, it's going to look like a line. Locally, in a very small window, it looks like a little line segment. It's actually a bunch of little line segments. All right, so what do you want to do, Kaylee? -2, which one has the steeper slope? 1 or 3?
3.
Try again. Yep. Don't you think it's steeper at 1? Like if you had to go downhill, like wouldn't that be like your biggest hill? All right, so at x equals 1, we have a slope of -2. All right, Kaylee, call on someone.
Well, you know that 3 is negative.
Okay. So by process of elimination, the only other negative slope happens at x equals -3. All right, Betsy, call on someone. We now have 1, 2, and 7, all positive slopes, and we have to compare magnitudes. And I think there might be debate over one of these. I'm not sure.
Gabby.
It's like, would x equals 0, that'd be 7. That's the steepest slope.
I totally agree, and that's not the one I thought we were going to have a debate over. So I think Gabby picked a good one to do next. It's steep at x equals 0, so that's going to go with 7. All right, Will. Debatable. Let's see what we have.
C was x equals 2.
So at x equals 2, you think the slope is 1. And so by process of elimination, you think that the slope at x equals 4 is 2.
I think it's the other one.
Yeah, me too.
Sorry, I don't know what's going on with this screen.
Well, like, if you draw the lines like that, you could, 2 looks...
I'm sorry, that's a lot. At x equals 1.
No, actually, it's 2.
I would say that
Two are 4.
they look pretty comparable.
But they're not parallel, so...
No, they're
That
not.
one is tilted a little bit.
Yeah, I think x equals 2.
I'll tell you what I thought was a good argument. Rachel Johnson in the other class said, look, x equals 4 looks like it's closer to the bottom of that hill, closer to the valley. And she said, at peaks and valleys, what's the slope? At the top or at the very bottom? 0. So the closer you are to the bottom, the closer you should be to 0. So with her reasoning, people felt like, okay, x equals 4 had a slope of 1, and x equals 2 has a slope of 2. I think you could argue that it's not really all that clear cut. Like, do you understand how it could be debatable?
Yeah.
All right, but I liked Rachel's argument. I was like, all right, if you think about it that way, it's, that pretty much does say it. All right? Questions about that? You sort of like that. Isn't that sort of fun? It's like a math puzzle, right? All right. Who says you don't play games in math class? Have you noticed that the older you get, the fewer games you get to play in math?
Yeah.
It's a bummer, huh? Or is it just because you've had me 2 years in a row? Sorry, I'm looking at Kaylee and Adrian and Gabby. And Tolly. All right. Let's put these in order. We want to put these in order from smallest to largest. Slope at 0.2, slope at 1.5, slope at 1.9, the number 1, and the slope connecting the points between 1.5 and 1.9. All right, should we put maybe some points on this, estimate some points on this graph maybe? Let's see. I'm going to guess that this is 0.2, right around there. 1.5 looks like it's probably around there. 1.9 is maybe around there. All right, so who wants to start with some observation that maybe we could make? I'm not saying we have to put them in order yet, but an observation would be helpful. Zach? Slope here is 0. Uphill or downhill? Increasing or decreasing? Uphill. So the slope is... Say it loud and proud because the alarm... Positive, right? So the slope is positive. I agree. We know that this number, whatever it is going to be positive. As a matter of fact, if I had to draw in a line, it'd probably have a slope... I don't know. How steep would you say that is? Can you tell? That's a great... All right, so Zach actually is leading us to a next question, to compare A and E.
Because when you go up one, actually not even
No,
go
it's so
over.
steep though, because there's 1 and there's 1. It would
So-
have to be almost like this.
Less than
It would
one.
almost have to be a perfect diagonal,
So-
almost like a square.
Up 1 and over 1 is like that.
Yeah, so it's not. It's much higher. It's like
It's
3
much
or 4.
steeper.
So it's steeper
It's much
than
steeper.
1. All right, so can we agree that...
Sorry to be obnoxious.
No, please.
I think I can do this in a physics way. Kind of. So when you launch a projectile, isn't that point that's perpendicular, like what you just drew at point 2?
Mm-hmm.
Like isn't that
That'd be like the initial
I
velocity.
forget, but, yeah.
Okay.
But like,
And if you wanna
I
think-
remember doing physics graphs and we would like do that.
Yeah, and as a matter of fact, you would tell me that the velocity at the top is 0, right? And that as it comes down, it's speeding up. So the velocity down here is going to be greater than the velocity here. And really what you're saying is the slope here is more negative than the slope there. So it is a physics way. It's okay. And that's not obnoxious. That's good. That's a good thing to be able to do. So would you agree that A is going to be greater than E? Like,
Yeah.
so A probably ends up here and E ends up here because we're going smallest to largest. Whoops. Oh my gosh, I don't know what's going on. So here's the small end. Oh. Alright. Alright, so, I mean, do you know which one's more negative? C or B? C is more negative, and then B. And then the question is,
Oh, wait, you're just putting them from great. This number of false, but you don't have to actually say what you
no, it just says put them.
Oh.
And then the only remaining question is, what can you say about the slope between 1.5 and 1.9? If you think about the skier, you can tell me exactly where D should go. Say it loud and proud so we can all leave.
In between C and B.
D is the average of C and B. Hey, we did it. Nice. Way to be, guys. All right. Hey, have a wonderful Wednesday. Have a great afternoon.
Now, do we not have to write
Thank you.
velocity with the direction?
You're welcome.
Isn't that just speed?
We are talking about speed. Well, actually, downhill skier, so we're going down.
But we didn't specify that.
That's enough out of you.